Good morning, good afternoon, or good evening, whatever time you're watching this video, take the appropriate greeting. Just before we kick off with Module 3 today, I want to just highlight some bits remaining from Module 2. So I've put some solutions available on the Blackboard site, so please go over the problems. And these are from Chapter 17 of Medicine. And I told you where you can get copies of Medicine from last lecture. I've put solutions up for two of the questions that are going to be particularly pertinent for your understanding. So I've put up 17 points, I think about 17.1 and 2 up there, or 1 and 3. Those are up. What I'd advise you to do is attempt before you go through the solution. Because otherwise you won't learn anything. There's a couple of more questions on there that I advise you to go through, 17.6 and 17.8. Now both of these are effectively, they are barely open sections, I'll say. So the sections that have been cut, or the sections that have actually got an infinitesimal gap in it. So they're open sections. You're being asked to determine the shear centre. Now I would like you to do it for both closed and open. Okay, this is not what's actually written in the textbook. He asks you to only look for the open ones. I'd like you to get both the closed and the open. And I'll provide some solutions for that this weekend, or next weekend rather. The reason that I'm asking you to do these is because all of these problems going together are going to fundamentally build into your first big homework for this course. That's going to be given to you on the 17th of February, and I'm going to give you just under 2 weeks to do it. Okay, I might even give it to you, I'll say before, because I might give it to you on the weekend just before the 17th of February, but this is going to be due on Sunday, March 1st, 23:59 hours. You'll be emailed your homework. It'll be emailed to you and it'll be an individual exercise. So I really advise you to go through those examples from my notes, where I've taken some of them from Megson. The examples from Megson that I told you to go through, particularly 17.1 and 17.3 and 17.6 and 0.8. If you can go through those and you can understand those, you will be golden by the time you get to your actual proper homework. Let's go into, now we're in Module 3. And we're looking at statically indeterminate truss structures. So let's just remind ourselves what makes a structure statically indeterminate. So we've got three numbers that we need to remember. We've got M, J, and R. M is the number of members. J is the number of joints, or the number of nodes. And R is the number of reactions. And I'll put brackets there, unknown reactions. So, if R is greater than 3, then we are externally statically determinate. sorry, externally statically indeterminate. On the other hand, if we've got R can still be 3 or less, and we can still have a structure that we can't solve internally for all of the forces, and that's if we've got So this is the requirement for internal static determinacy. As long as you've got m is less than or equal to 2 times the number of joints minus the reaction forces, that allows us to solve for all of those internal forces using the force method. So we're going to focus on this one first off. We're going to focus on how to solve for externally statically indeterminate structures, and then we're going to move on to this one here. We're going to how we can determine the forces present in structures when they're internally statically indeterminate. So for this method here, you guys will have solved this a little bit before in 302, I think, or sorry, in 202. We used the force method. So let's just go through a reminder of the force method. We're still going to be using the force method, we're just going to be solving it slightly differently. So let's say, for example, I've got a pin-jointed truss frame, and I've got some unknown force here, and I've got 2 built-in supports. I know that for this structure I'm going to have 4 reaction forces. Okay, so I have 4 reaction forces, which means that it's externally statically indeterminate. So how do we solve this? Let's just remind ourselves how we use the force method. So 1, we pick a redundant support. 2, we remove it. And then we solve for this new equivalent structure. And we'll call it the reduced structure, because that one's now going to be externally statically determinate. 3, we see how much the whole structure moves in the direction of the force that we removed. And then 4, we determine how big the redundant support must have been to stop that movement from happening. And this then means that this gives us a known reaction. And then we add that reaction back in and we solve for the real structure. So this is a method you guys will have used before. We're still going to be using it in this course, so I need you guys to be familiar with it. So we're going to go through a quick refresher example. The bit that we're going to change around a bit is this bit here. See how much the structure moves in the direction of the redundant reaction. Because this bit can be really complicated, and we're going to introduce a new methodology to help us determine this rather elegantly. And when you get your head around it, you're going to think, oh man, I wish we'd known this before. Or at least I hope that's what you'll think. So let's just remind ourselves. So if we have a structure like this, again, this is taken from the notes, so I want you guys to be able to go through it and understand it. And in the notes, I'll go through this in complete detail. So we have an externally statically indeterminate truss structure because we know we've got 4 reaction forces because they're built in. We've got FCY, FDY, FDX, and FCX. So in this structure, I've chosen arbitrarily to set this one equal to 0. That's my redundant reaction. So what that has in effect done, in fact, sorry, this next one I just marked here, but what that's effectively done, it's replaced that with a roller support. And you don't need to draw it like this, but it just helps you to visualize what's going on. So it makes sense that if we're loading in this direction, we would expect this structure to shift towards the right-hand side to increase it in the direction of x. So the first thing is we solve for all of those, we solve for all of the reaction forces. So you guys should be able to do this step, just check you can do it. So this is from the sum of forces in the x direction equals the sum of forces in the y direction, which is equal to sum of the moments anywhere must be equal to 0. So we can solve for this, okay? Check you guys can do that at home. And we then solve for the internal forces. So the way that we do this is, again, using the method of joints. And at each node, again, we have the sum of forces in the y direction is equal to the sum of forces in the x direction is equal to 0, okay? So we can determine, using this method, all of the internal forces of this representative structure. We then use the compatibility relationships to determine how much things are going to move by. So this step might be a little bit of revision here. If we've got a bar element, so this could be for any truss frame, we've got a 2-force member subject to a force P. This is going to be extended to some new length, so it's going to be L plus delta L. And from Hooke's law, we know delta L is equal to P multiplied by L divided by E divided by A. So we've got Young's modulus, cross-sectional area, original length, force applied, and then we've got the increase in length. Okay, so for here, we can then work out the length of all of these members. So the one on the bottom is under tension. I've drawn those as arrows going towards each other. The one at the top is under compression, and these are under tension. So we know that when we've got a tensile force, members AC and members AD must be getting longer. Okay, sometimes confusing because the arrows are going in the direction of the internal force there, but these are going to extend, and this one is going to contract. So for this member here, we could ultimately unpin all of these members, and then we could work out what sort of triangle they've got to be to go back together. And in the notes, I go through that in full. We could be smart really here, and we could say that actually the extension in this direction has to be equal to the extension of member CD. Okay, and we could work it out from that method. So we know the structure moves, and we've got this displacement force here, CD. Sorry, I mean that member CD has, let's make that a better pen. Member CD is L plus P multiplied by L on EA. Okay, because that's just, I've taken this from up here and moved it down here now. So the amount that we're moving in that direction now, the delta dx direction, is equal to P multiplied by L on EA. Okay, so that's the amount that we are moving. In fact, let's not make that a small delta, let's make that a big delta. That just keeps this consistent with the notes. So this is the amount that our structure moves. Again, I'm hoping this is somewhat revision, so I'm going through this rather quickly. But if this is the amount that the structure moves without FDX, we need to make FDX large enough to move it by delta dx equal to delta dx. So this is the displacement due to f dx. Okay, and this is the displacement due to p. So if we take this structure now again, we would just draw our structure down here. We've got our one built-in, one roller, and instead of having the external force P being applied, let's draw this completely. We don't apply the force P, we apply a 1 Newton force in the direction of Fdy. We're then going to have a look at the reaction forces. We could solve for the reaction forces. We've got 3 again. It should be apparent from this that actually there's only a single member that can take this load. So these are all zero force members for this case, and there that FCD is going to be equal to 1 Newton in this case. So we could say that the displacement in this member due to a single unit force, delta dx, is equal to 1 multiplied by L on EA. Amount D moves to left with F dy is equal to 1 Newton. So the absolute size of F dy has to be enough to make this equal to this. So we can say PL on EA, remembering this has come down from up here, it's got to be equal to F dx multiplied by this. And we'll easily see F dy is equal to P in that case. Sorry, F dx is equal to P in that case. Now you should see here, and it should be obvious that the way that I've drawn this, I drew this 1 Newton force going to the left, which would actually be a negative 1 Newton force. So this should actually be a minus P in this case. And then we take this minus P and we put it up here. This gives us the now known external force. So we've got this structure here, we can solve for our other reactions, and we can then solve for all of the internal forces. So this is now this problem solved. We've solved for a statically indeterminate structure when we've got a redundant external support. So the method is valid, and it's the method we're going to use. Where it becomes difficult is this one was a little bit easy because we could see that this bottom member can only, the movement of node D is equal to the extension of this bottom member. If we'd had to actually go through and unpin them all completely and work out the displacement due to geometry, then it would be a whole lot more complicated. So we need a better method to work out these displacements, and that's what we're going to be coming up with. This problem here, this is the one that we're ultimately going to try and solve. So it's statically indeterminate externally. Again, we can see there's going to be a, well, let's just draw these all on here. No, it's only got one reaction there, so it will have an FBX, FAY, FAX, and there'll also be an f dx in here. So again, we've got more external reactions that we can cope with, more unknown reactions. So for this one, clearly we're going to have to pick another one of these to be a redundant reaction. We're going to remove this one, but then we need to determine the displacement of this, effectively where this whole structure will move in this direction now. Now we could do this again, like I say, with the geometry method. This becomes very, very complicated, and I certainly wouldn't like to try and solve this problem. So we're going to introduce a better method to try and cope with this. So I'd like you guys to go back through the force method, look in the accompanying notes, and I explain the previous example in quite a lot more detail. Just make sure you understand the problem that we're solving there and quite why that would be so difficult for this problem here. We could do it and we could work it out, and if you're really tenacious, I'd encourage you to give it a go. But ultimately, to get this displacement, we need a better method. And that's what we're going to come up with today. So we'll say it's a more elegant mean to get displacements. If we're using the previous method and we're just trying to work out displacements based upon geometry, we're relating stiffness and deformation. So that's our governing set of equations. It's Hooke's law, and it's valid and it works. But we can think in terms of work and energy instead. And the governing equation that we're going to use will say that the work done by external forces is equal to the internal energy of the structure. Let's just think about what we mean by work done. So if we've got some sort of force and it's causing a deformation of a structure, we've got a force going through some displacement. That's work being done. So that work being done is energy is being transformed into the structure. And we've got this work being stored inside the body in the form of energy. That's all energy is. It's stored capability to do work. And we're going to try and get you to think in those terms a little bit more. So we can have a structure with multiple external forces. And we can obviously have structures with multiple members. And we'll write these down, and we'll say that if we've got a structure with P external forces, we'll use big P and little p there. Let's just make my little p look a bit better. We'll talk about external energy of member P, and then we'll do the same for the members internally. We'll have M members. We just add them all up together. Okay, so the sum of all the work done by all of the external forces has to be equal to the sum of the internal energy stored by individual members. So we've got this governing equation now, but we don't quite know what this means yet. So we're going to think about these two things. What is external work? And then we're going to think on the other side. I've swapped my colours around a little bit here. What is internal energy? And once we've got these definitions down, we can describe them equate the two and come up with displacements, because we can see here this one's just going to be a function, or we'll ultimately see this one is just going to be adding up forces multiplied by displacements internally. No geometry involved, except for in the force method, so except for in the method of joints. This one here is going to be adding up forces multiplied by displacements. So it's going to be easier to solve this than it is to use something like the cosine rule to work out the displacements in a complex truss structure. So I go through a much more full derivation of the accompanying notes about what external work is. But we're going to just go through a quick bit here. So I advise you to go through C section 3.3.1 in the accompanying notes. I spent a lot of time going through and writing that in with full diagrams and just explaining effectively the whole idea of what this external work is. But we're going to remember the displacement and the stress-strain curve. So recall our stress-strain curve. We know that it's linear, effectively. So it's linear at first, and we're going to operate just in this region of linearity. Instead of writing stress-strain, we could write force and displacement. And I know that as I increase my force, I increase my displacement. Now the interesting part of this curve for us is the area underneath it, which is equal to the amount of work done. So the area has the units of newtons multiplied by meters, joules. Okay, so that gives us our energy there. Now, to determine the area here, we can sort of see that the area is going to be equal to a half multiplied by force multiplied by whatever our displacement here is. So we say that if we take our final displacement as being big delta, our final force as being F, then this is equal to our external work done, okay, UE. There's another way we can look at this, and we can get this in a second method. So it's not always easy to see at first why there's a half here. So let's think about how we get to this point. So if I'm at this point here on my curve, I need to work out what this area is. So I need to integrate from big delta through to 0 of all of the force with respect to this ordinate. So I can write that as my external work is equal to the integral from big delta through to 0 of my force multiplied by d delta. Now my force is a function of my displacement, and the constant of proportionality is the stiffness. Okay, this then becomes k delta squared on 2. Now we know that k big delta is equal to our final force, therefore our total external work is equal to force multiplied by delta on 2. Okay, I go through this in a lot more detail in the accompanying notes, but this is the one that we need to remember. Our external work done is equal to the force multiplied by the displacement in the direction of the force, just remembering that from our definition of work done, divided by 2. So let's look at some examples of this. So in this example, we've got a truss structure, we've got a load P, and it will deform. We don't quite know how the structure is going to deform. It's probably going to look something like that, but we could determine for this structure that it's got one load. Our sum of external work done is simply equal to a half P multiplied by delta. Now delta is going to be the bit that we're going to solve. And we're going to be able to solve for that in the next couple of questions. Very similarly, if we've got two forces, remember we have to use the displacement in the line of the force. So for P2 here, we look at the displacement in the direction of the force, and P1 we do the same thing here. So for this structure, the sum of external work is going to be equal to a half P1 delta 1 plus P2 delta 2. Okay, that's our external energy solved. Or external work. It's pretty easy. We can get this external work done, and then we've got to equate it with the internal energy. So what is internal energy? I'm just going to put this up here. We'll put strain energy, because it's sometimes called strain energy in other sources. So think about what energy is, okay? Any form of energy, I said it a little bit earlier, is the potential to do work. And we can think about this being stored work. Okay, so gravity is the potential to fall, which is kinetic energy. Food is the potential to run. Okay, so kinetic again. And so on and so on. We can think about all these different forms of stored work. So for truss structures, we're looking at two force members, and we need to think about how this energy and where we get energy from in our structure. Again, we're getting this external energy. We can, through a very similar reasoning to how we looked at the internal energy, if we were to draw our stress strain curve again, but again putting it in dimensional terms of displacement on here, we'd be looking for the area underneath it. So we say that our internal energy, Ui, is equal to a half P multiplied by delta L, multiplied by the extension on here. Now our delta L is given to us by P multiplied by L divided by EA. The same as we would have worked out using the geometric method. So we can say that Ui is equal to a half P squared L divided by EA. Bingo. So this is our expression for internal energy of a two-force member within a truss structure. So we should be able to solve this now. Let me just dig out an example over here. So we've got a half P squared L. This is the structure that we're going to try to solve. So the way that we're going to solve it is by assuming this reaction is redundant. So we're going to redraw this. Well, I'm going to assume we've got the external forces solved now, so I'm drawing the internal structure now. Sorry, assume we've got the external reaction solved for. We would have got this from a free body diagram. And we're trying to look for the displacement. So our unknown reaction, we're going to say that we had f dx is equal to 0. So we want to look for whatever this displacement is here, which we'll call delta dx. So we look at our equation that we've just developed. We've got u, e, or the sum of ue is equal to the sum of ui. So we can look at the external work we've got on this structure. Now these aren't going to move here. We've got two displacements. We've got one here. So we could come up with let's do this here. Let's call this, what node is that? That's node C. Fcy. We know that our external energy is going to be equal to half 10 kilonewtons multiplied by, sorry, I've called the Fcy up there, I should have called it delta Cy. Let's call it delta Yc. And then we're going to look at whatever the external energy is going to, also the displacement is going to be here. Now this is a little bit difficult because this is 0. So we can't get the displacement here using this method. We can get the internal energy of all of these parts because once we've got this structure and we've reduced it to this determinate structure, we could work this one out. We can work out the P in all of these members, and we could then say that we've got a half. Let's just get our equation back again. Let's go on EA. So we've got half P squared L on EA, and we do this for, say, the first member plus a half P squared L on EA for the second member, and so on. Our issue comes here is that this method, as we've presented it so far, only helps us to determine displacements where we have a force, and this doesn't help us yet. So if we remember that UE is equal to a half F multiplied by delta, F cannot be equal to 0 if we want this to not be equal to 0. So we can't solve this just yet. I haven't introduced this for nothing though. We're going to effectively say, well, let's just imagine we've got a force taking place at D. So we're going to determine how we can effectively use a virtual force to carry it through. Okay, so we'll use a virtual force. I am not going to introduce that in a video lecture. This next part is quite a bit to get your head round, and I would rather be in class so I can see your faces and see whether you're taking it on board or not. So this is a little bit of a shorter introduction to this method so far. I would like you guys to go through a couple of examples from the notes. So I want you guys to go through, there's 3.3.2.2, a truss structure with 2 S's. Okay, and I solve for the external displacement of node B using this method. So I want you guys to go through this for Wednesday. So check you can follow it, check you can go through it, be confident that you would be able to do that. And then on Wednesday, we're going to solve to work out the full displacement of a structure where we don't have any forces using the virtual work method. Okay, as always, drop me an email if there are any questions, and I will see you all in class on Wednesday.